Hello, everybody. Welcome back to the undergraduate seminar. We've got Anatoly Zavyalov who's going to tell us about automatic sequences. Thank you for coming out and speaking. Anatoly, take it away.
Yeah, thank you very much for having me here. So my name is Anatoly Zavyalov. Oh, wait 1 second. For some reason, I can't switch to a new slide. There we go. I'm a third year at U of T at the St. George campus. I study math, computer science, and a little bit of physics. I've been doing research in automata theory since summer of 2022, and I've previously done research in astronomy as well. For fun, I like to play piano and I make video games as well. So the structure of this talk, I'm going to just generally introduce the area of automata theory. So I'm going to define what deterministic finite automata are. I'm going to define automatic sequences, and then we're going to look at some examples of applications of automata theory and automatic sequences, and a very special automatic sequence called the Thue-Morse sequence, and some applications of that, as well as transducers, which are a way of obtaining more automatic sequences from ones you already have. And we're also going to discuss what happens when you go beyond the standard way of representing numbers in base K or in binary, for example. So to start, to just motivate the idea of automaton, suppose that you're getting on a bus, and suppose that bus fare costs 25 cents. In reality, it's like 15 times more than that, but just suppose it's 25 cents, and exact change is needed. And the only types of coins we have in the 1920s, the only types of coins that we have here in Canada, aside from loonies and toonies, we don't have pennies anymore. So there's only 5 cents, 10 cents, and 25 cents that we can use. And in what ways can you pay the fare? Well, you can obviously just give 25 cents. That works. You can also do 5 cents, 5 cents, 10 cents, and 5 cents. That adds up to 25. Or maybe in a different order, 10 cents, 5, 5, 5. But you can't do 5 and 5 because that doesn't add up to 25. Here, epsilon means just giving nothing. If you don't pay, you can't get on the bus. And if you overpay, so if you pay 10 cents, then 25 cents, because exact change is needed, that's also not going to be accepted. So we can represent this kind of decision procedure using something called a state machine or an automaton. So here we have just some states which represent how much money have we input so far. Starting off with 0 cents, if we put in 5 cents, then we increment by 5. If we put in 10, we can jump over by 10, and we can go directly to this 25 state by inputting 25 cents. And once we reach this kind of double circle state, that means it's an accepted state, and we can get on the bus. Just some notation that I'm going to be using throughout. I'm going to say sigma is an alphabet. It's a finite, not empty set. And sigma with a star on top, so sigma star, denotes all the finite words that you can make over sigma. So that just means any arbitrary concatenations of symbols in sigma. So if sigma is 0, 1, then sigma star would just be the empty word and any binary string. And if x is a word, then putting absolute values around it denotes its length. So the length of 0, 0, 1 is 3. And here I'm giving a very straight up definition of a deterministic finite automaton, but really all it is you, just like how we had it in the previous example, we have a set of states, we have a transition function, we have some kind of idea of an initial state, and we also have a subset of our states being accepting states. So once we reach those, we're accepting. So we have some states, we have some kind of input alphabet that we that our edges are labeled by. We have an idea of how to get from one state to another through a transition function. We have an initial state, and we have a subset of our states as accepting. So, and deterministic finite automaton accepts a word if when you pass it through the automaton, you end up at a final state. So for instance, over here, 5, 5, 10, 5, that's accepted. But something like 10, 25 isn't accepted because that doesn't go to a final state. So let's just briefly take a look at a simple example. Here we have an automaton of 4 states. It has a lot of different cycles. But we want to determine what kind of strings can we put into it such that this automaton accepts those strings. So if we look at, say, 0, 0, 0, we start off at this initial state over here. We put in 0 that goes to this state, another 0 goes to back or to an initial state, and another 0 ends us at an accepting state. So 0, 0, 0 is accepted. Something like 0, 1, 0, 0, 0, 1, 1 is also accepted if we just follow the edges again. So 0, 1, 0, 0, 0, 1, 1 will end us at this state, which is accepted. But a rejected string looks like, for example, 1, 0, 1, 0. That just ends up at our initial state, which is not accepting. Or 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. That's ends us up at that state, which is also not acceptable. And if you think about it, you can kind of see that whenever we add a 1, the second number gets flipped. And whenever we see a 0, the first number gets flipped. So we're really counting the parities of the number of zeros and the number of ones we see in the string. And a word is accepted if and only if the parity of the ones and zeros doesn't match up. And by the way, if anyone has any questions, feel free to interrupt or type them into chat. I have the chat open right here. And deterministic finite automaton, they can be used as a computational model. If you think about it, they only remember one piece of information, and that is the state that they're on. So they're like Turing machines have like an infinite tape, but these automata, the only thing they have is just an idea of what state they're currently on and how to get from one state to another. And they're very simple, but they can be used to solve seemingly difficult problems. So one example we're going to look at is determining whether a number is a sum of 3 squares or not. So Legendre's 3-square theorem says that a number is a natural number is a sum of 3 squares of integers if and only if it is not of the form 4 to the a times 8b plus 7, where a and b are non-negative integers. And our goal is to make an automaton that will read in a binary representation of n and accept that binary representation if and only if n is a sum of 3 squares of integers. So to do this, let's examine what this thing is. So suppose that a number is of this form, so it's 4 to the a times 8b plus 7. What can we say about its binary representation? So if we just look at 8b, whenever we multiply any number by 8 in binary, that's the same thing as just adding on 3 zeros to the end of it. You have some, whatever the binary representation of b is, followed by 3 zeros. And if we add 7, 7 in binary is just 1, 1, 1. So we have whatever, and then 1, 1, 1. And when we multiply by 4 to the a, in binary, that's the same thing as adding on an even number of zeros. But that even number could be 0, because if a is 0, multiplying by 1 doesn't change anything. So we could still be in this form. And we can actually we can make an automaton that recognizes words of this type. So we basically just want an automaton that when it sees 1, 1, 1 followed by an even number of zeros, to accept. And here's how that automaton looks like. And let me explain how it works. So let's say we start off at the initial state here. The initial state is denoted by this arrow going into it. And we read 1, 1, 1. Well, if we read 1, 1, 1, it's of this form, right? Because you could have no zeros here and that would still be even. And if we read 1, 1, 1, that's an accepting state because it's of this form. And if we say put in 0, 0, we'll follow this edge, 0, and then 0, that would lead us to another accepting state. And if we keep adding an even number of zeros, we'll just be cycling in between these states 4 and 5. And whenever we have an even number of zeros, it'll accept. But whenever we see like a 1, we're not supposed to have a 1, so we go back to one of these states. And then, but if we see 3 consecutive 1s and then an even number of zeros, that'll end us up at either this state or that state. But remember that it's of this form if n is not a sum of 3 squares. So we want an automaton that accepts if it is a sum of 3 squares. So to basically, we want to flip this around. And what we're going to just do is say everything that is an accepting state is no longer an accepting state, and everything that is not an accepting state becomes an accepting state. So that's exactly what we do. And this automaton will read in a binary representation of n and accept if and only if n is a sum of 3 squares. Which I think is like really cool. Like you only need 6 states to determine whether n is a sum of 3 squares, which initially, if you just write that out, like, and if you write it out like this, like how would you even approach, oh, that just opened something for some reason. Okay. When I double clicked, that was weird. But how would you even approach this? But it turns out it can be recognized by an automaton of 6 states, which is, I find, pretty cool. And right now, what we have is an automaton that just says, okay, some states are accepting and some aren't. But what we're going to do is we're going to generalize this notion to, instead of saying, can it be done with fewer than 6 states? No. So that is actually the smallest automaton that can recognize whether or not n is a sum of 3 squares when you feed in the binary. If you feed in in a different base, maybe. But in binary, this is the smallest automaton. How do I know that it's the smallest automaton? Well, you can prove that an automaton is minimal. So, and there are algorithms for minimizing certain automata. And the way that this automaton was actually generated was using a piece of software called Walnut that I'll touch on briefly at the end. But it runs these automata through minimization algorithms. Yeah, so one of those algorithms is called Myhill-Nerode. Like the Myhill-Nerode theorem allows minimizing automata, but that's outside of the scope of this talk. So what we're going to do is we're just going to, instead of now having accepting states and not accepting states, every state is going to have an output into some other set. And we say it's a deterministic finite automaton with, oh wow, why did it do that? Okay, that's crazy. We're going to say it's a deterministic finite automaton with output if instead of having just a subset of accepting states, we have an output alphabet and some output function, which we call a coding. So how that looks like is now we no longer have these double circled states. Now we just have the our outputs of the states are listed right beside the name of the state. So for example, if we feed in some kind of string binary representation of some number, and we end up at the state like 2, 0, then the output of the automaton would be 0 on that input. Or if we end up here, it would be 2. So it's no longer accepting, or not accepting. Now it's some kind of output. And we can think about what happens if we start plugging in numbers into this thing, like binary representations of numbers, like how we did it in the Legendre's 3-square theorem example. What would happen if we just plugged in numbers and see what we got? And if we did this for every natural number, we could get a sequence out of that. So, and that's exactly what an automatic sequence is. So don't worry about trying to understand all of this. What all of this means is just you feed in a number into this kind of automaton with output and just see what you get. And if you do this for every natural number, so the nth term of the sequence you get is just plug in n in base k, where k is just whatever input alphabet you have. So here it would just be 0 through k minus 1, and just see what you get. And that will be the nth term of your sequence. So, and if you're given a sequence and it can be computed this way through an automaton, like there is an automaton that computes the nth term of the sequence when you plug in the base k representation of n, then that sequence is called k-automatic. That's what an automatic sequence. So let's just look at an example. Here we have an automaton that consists of 2 states. Starts off with this initial state, and here over here I had like the state name and the output. When I omit that, 0 is just the output and 1 is the output of this state. So what I'm going to do is I'm going to go through some natural numbers, plug them into this automaton with output, and see what I get. And whatever I get is going to be building up my sequence. So if I want to get what is the 0th entry of the sequence, I'll just plug in 0 here, and that just goes and loops here, and we get 0. If I want to plug in 1, I'll just plug in 1, and the output of the state we end up at is 1. And the second term of the sequence would be if I plug in 1, 0 into this automaton. So 1, then 0 ends you at 1. And I could also plug in 1, 1, which will end up at this state, which has an output of 0. And then 4, binary representation is 1, 0, 0. And you can see the pattern. You just keep going. So 1, 0, 0 will end you at 1. 5 will end you at 0. 6 will end you at 0. And 7 will end you at 1, and so forth. You just keep plugging in binary representations of this, and out of that you get a sequence. And this automaton is very special. The sequence that we got, it has a name. It's called the Thue-Morse sequence. And if we think about what this automaton is really doing, we're reading a binary representation of a number, and whenever we see a 1, we flip the output. And whenever we see a 0, our output remains unchanged. So the state we're on stays the same. So if you read in an odd number of 1s, you'll end up at this state 1. And if you read in an even number of 1s, you'll end up at the state 0. So we're really counting the parity of the number of 1s in the binary representation, or we can just think of that also as summing up all the digits in binary and looking at the mod 2. And this sequence actually has a lot of really cool applications. And one of them is in fairly sharing things. So let's say Alice and Bob are dividing things that are of non-increasing value. So let's say they're captains in and they're picking players for their soccer team during recess or something like that. What is the fairest order for them Yeah, fantasy draft. What is the fairest order for them to pick? Well, the kind of naive way would just be, let's say Alice picks first, then Bob, then Alice, just alternate, A, B, A, B, A, B. But clearly, Alice has an advantage. If you look at every pair of items, Alice will always pick the better one. So, okay, Bob comes up with an idea. What if we, after AB, what if BA? So now on the next pair, Bob will get to pick first. Well, if we repeat this, like if we have more than 4 things, when we repeat this, then Alice still has an advantage because for every 4 items, Alice will get to pick the best one. So, okay, what if they swapped order again? So after ABBA, they did BAAB. But then again, every 8 items, Alice has an advantage. So let's keep flipping the order. And this right here, if you replace A with 0 and B with 1, you get the two-way Morse sequence. So, and let's just see what we did. We started with A, then we copied whatever we had in before, and we put it at the end, and then we flipped it, so it became a B. And then we did the same thing. So we copied it and flip it, get A, B, B, A. Keep doing that, and do this forever, we get the two-way Morse sequence. And this is an equivalent way of constructing it. But okay, so I did all this, but does this actually work? Like, is it better than just picking A, B, A, B, A, B, A, B, just alternating? Well, let's suppose that if the value of your items that you're picking is constant, so it doesn't change, then if you just go with this A, B, A, B, A, B, A, B method, then here, if Alice is blue, then she always either stays on top, but never goes below Bob. And if you take an average, then Alice will always stay on top. So it's so Alice definitely gets an advantage here. But if you apply, if you pick in the order of the two-way Morse sequence, you'll actually see that Alice and Bob, they swap. And if you take the average, it kind of converges. So at times Alice is better, but at times Bob is better. But if you average it out, it's pretty fair. And if the value of the items is decreasing, then again, if you just pick naively, like just alternate, then Alice will always stay on top. But if you pick in the order of the two-way Morse sequence, then again, at times Alice will be better, Bob will be better, but eventually it will converge. So I find this really cool. So whenever you're, I don't know, whenever you're back in elementary school and it's recess and you're picking does this hold for non-monotonic values? It might, but if you try, for instance, so I got a question in the chat, does this hold for non-monotonic values? And it might, but oftentimes it will not. It also depends on how fast the value of the items is decreasing. If it's decreasing exponentially, like then the person who picks first will just have a significant advantage by default because the person that picks second can never catch up. So if you here it's just decreasing at a constant rate, but if it's decreasing exponentially, then in certain scenarios it won't work. Let's look at another example, which is chess. So I'm sure a lot of people here have played chess. And if you have, then you know that there is a threefold repetition rule, which states that if the same position on a chessboard is reached 3 times in a game, then the game is declared a draw. And with this rule, you can figure out that you can't have infinite games because there's only finitely many pieces on the board, finitely many squares, so finitely many positions. And eventually you're gonna, if the game is long enough, then you're gonna have positions that repeat inevitably. But consider a slightly weaker version of this rule. So this was an official rule up until late 1920s. If the same sequence of moves is made 3 times in succession, then the game is declared a draw. So instead of the same position being reached 3 times, if the same sequence of moves is made 3 times in a row, is it still the case that we're going to have where we can't have infinite games? And it turns out that you can have infinite games. Like, that's why the slide is called that. And this was actually proved by, I'm going to butcher this pronunciation, Max Owe, who was a Dutch mathematician and former chess world champion. And he showed using the Thue-Morse sequence that with this weakened rule, you actually can have infinite games. And a property of the Thue-Morse sequence that allows us to show this is the fact that it is quote unquote cube free. And what that means is if you take any chunk of the Thue-Morse sequence, it will never repeat 3 times in a row. So for instance, if we say we pick 0, 0, 1, we're never going to have 0, 0, 1, 0, 0, 1, 0, 0, 1 appear in the Thue-Morse sequence. And we can use this property of the Thue-Morse sequence to construct our infinite game. So how we're going to do it is we're going to map, I'm going to say 0 and 1 corresponds to some sequence of moves. And here 0 will correspond to taking the knights on the left side of the board and moving them out and then moving them back in. So knight c3, knight c6, knight c3, knight c6, knight b1, knight b8. We'll just move the knights on the left side of the board out and then move them back in. That's going to be 0. And then 1 is going to be the same thing, except with the knights on the right side of the board. So knight f3, knight f6, knight g1, knight g8, we'll just move the knights in, then out. And an important characteristic of these moves, these sequences, is that at the end, the board remains unchanged. So when you move the knights in, then out, then the board is unaltered. And if we, yes, the rule change actually happened after the proof. That was so I'll get to that, yeah. So, and if we repeat these moves in the order of the Thue-Morse sequence, then because you're never going to have any chunk of the Thue-Morse sequence repeat 3 times in a row, no sequence of moves will repeat 3 times in a row. And if you just play with this following the Thue-Morse sequence, you're going to have an infinite game, which I was baffled when I first learned this. And yeah, so after, yeah, what an exciting game. Yeah, very exciting. So after Max Owe proved this in 1929, and he actually independently discovered the Thue-Morse sequence in his proof, then the chess rules were amended to make the threefold repetition rule what it is now. And with the current rule, you can't have infinite games. So yeah, so you get a lot of, yeah, so obviously a bunch of zeros here repeat, like after you're bound to have repeating zeros. and repeating once. So with the current threefold repetition rule, this would be a finite game. But if every sequence of moves happens 3 times in a row, then it's infinite. So now I want to talk about transducers. And how I'll motivate them is, so when we had automata with output, we had outputs on the states. And then when we fed in a string, we just fed it in completely and saw what the final output of the state we ended on was. But what if we put them on the edges instead? And what we're going to do is, as we feed in a string into this transducer, we're going to write down the outputs of the edges that we pass through. So here I might actually want to make use of this annotation because just to see how this will work. So let's say I have the string 0010, and I want to pass it through this transducer and see what I get. So starting off at the initial state, we would read in a 0, and we'd go through this edge, and we have an output of 0. So that's what this means here. So our output would be a 0. Then we go back to the state, and then we read another 0. Our output would be again a 0. But when we see a 1, now we follow this edge. We write down a 1 because that's the output of this edge. And then we see another 0, so we follow this edge and we write down another 1 because that's the output of that edge. And we just keep doing this. So let me stop annotating. Let me actually clear it. There we go. And so a transducer is pretty much very similar to an automaton with output, except the only thing we're changing here is we're changing some of the names of these things, but we still have the state, we still have the input alphabet, we still have a transition function, initial state, but now instead of having the outputs on the vertices, we now have them on the edges. So on a vertex along with an element of the input alphabet. So let's take a look at, is this an adder? Yes, so I'll actually talk about that. But you're right, that is an adder. So let's take a look at a specific example here. This transducer, what it does is it calculates it computes the exclusive OR of consecutive bits, with the first bit always being 0. So to see how it works, I'm going to annotate again. Let's say we have some sort of sequence, it doesn't really matter. And we feed it through this transducer. So starting off at the initial state, we're going to follow this state. The output of it is a 0. Now we're on the state 1. We read another 0. That's 0, because the XOR of 0, 0, 0. But when we see a 1, we'll follow this state, follow this transition, which is an output of 1. And then when we see another 0, we'll follow this transition, which has an output of 1. So the XOR of 0 and 1, whoops, that I looked at the wrong one. The XOR of 0 and 1 is 1, and the XOR of 1, 0 is 1. And now we're at this state, so we see another 1, and then when we see 2 consecutive 1s, we'll follow this transition, and that outputs a 0, and we just keep going. And what we're going to do is we're going to just take the XOR of the Thue-Morse sequence. So we can actually take an infinitely long sequence, like the Thue-Morse sequence, and put it through this transducer and see what kind of sequence we get. So you would just do exactly as I said, where you just pass through the sequence through this transducer and write down the outputs of the transitions that you take. And we get this new sequence. And going back to our original example of a transducer that I put up at the very first slide, this transducer, as Calvin correctly pointed out, adds up the bits that you read and mod 2. So again, you can see the 0 and the 1 the states correspond to what the current parity is, and when you read in another character, you'll just write down what the new running sum is. So the output of the transition will be whatever the new running sum is. So for instance, if we have 0, 1, 0, 1, 0, 0, 1, when we pass it through, we'll see, okay, we start off with 0, then 1, then 0, then 0, then 1, then 1, then 1, then 0, and keep going. So we just pass them through, write the states down, and we get this new sequence. And if we take the Thue-Morse sequence, again, we can write down what its running sum is by just passing it through this transducer. And one of the things I discovered this year is if you keep doing this, if you keep taking the running sum of the running sum of the running sum, so you start off with just the Thue-Morse sequence up top, and you take its running sum, and then how you get these later running sums is you kind of how in Pascal's triangle you look at the number on top and the number on the left and add them up modulo 2. Look at, like, for instance, 0 plus 1 is 1, 1 plus 1 is 0, and so forth. And if you keep doing this, and then let's say you want to be creative, and let's say we want to make an image out of this. So let's say 1 is a black pixel and 0 is going to be a white pixel. And you do this like hundreds of times, you'll get something that looks like this. If you look at just if you do what I said in the previous slide, where you just add up whatever was on the left and on top, and then add them up modulo 2, you get these kinds of Sierpinski-like fractals. You get these Sierpinski triangles embedded in Sierpinski's triangles. And this was discovered before. I just independently discovered this. And a good question to ask is, well, why does this happen? Like, where does this come from? And if you have seen the Pascal's triangle mod 2, I don't have an image of it here. I wish I did. But you'll actually just get the Sierpinski fractal again. So if you, instead of starting off with the Thue-Morse sequence up top, if you just start off with 1, 1, 1, 1, 1, just all ones, and then do this same exact thing, that would just give you the Pascal's triangle mod 2. And it gives you, I want to stop annotating. It's not letting me. Okay. And if you do that, you get the Sierpinski triangle. And if you do that for the Thue-Morse sequence, you also get these Sierpinski-like fractals. And right now, I'm looking into how do we, so we can just compute these rows manually and put them into an image. But if I want to, say, take an arbitrary k and figure out what is the kth row of this going to be? What is the kth running sum? can we get an expression for it? Like a nice expression. And another more important question is, can we get an automaton that with output that computes the kth row? And right now we only know this for the case where k is a power of 2. So I proved exactly what it looks like when it's a power of 2. Unfortunately, that's still unpublished, so I'm not going to go into too many details about that. So yeah, I found this cool. I actually discovered this while writing on the TTC. I wish I had a picture of it here, but it was mind-blowing. Okay, so and I'll finish off by talking about right now what we've been dealing with is looking at numbers in binary or base k in general, where we represent numbers as sums of powers of k, and binary we represent them as sums of powers of 2. But we don't really have to do this. Like, we could write numbers as in different numeration systems, for example, Fibonacci. And what this means is, so yeah, the Fibonacci numbers are defined by this recurrence relation, where I'm going to say that the 0th term is 1 and the f of 1 is 2. Sometimes you write 1 and 1, but it doesn't really matter. And you can write, I'm just asserting this, you can write any number as a sum of Fibonacci numbers. So just like how we did it in base k, where we wrote, like, in binary you write 1, 0, 1, where it's a 1 if you include a certain power of k, or a power of 2. We do the same thing here. Di is either 0 or 1 if you include the ith Fibonacci number. But this decomposition isn't unique. So for instance, you can write 14 as 13 plus 1, but 13 is also 8 plus 5 plus 1, right? And you could keep doing this. There's a lot of ways to write numbers in terms of Fibonacci numbers. But to make these representations unique, we kind of enforce that you can't have 2 consecutive Fibonacci numbers in the sum. So for instance, 8 plus 5, we're going to write that instead as 13. Or 3 plus 2 as 5, and then 8 plus 5 is 13. And if we look at this Fibonacci representation, we will write it like this. Here, this just means this one refers to the Fibonacci number 1. All of these other Fibonacci numbers, so 2, 3, 5, 8, are 0, but 13 is also included. But you can equivalently technically write it as 1, 1, 0, 0, 1, but here we have two consecutive Fibonacci numbers, so we forbid that. And this restriction is equivalent to saying, just 1, 0, 1 is the same thing as 1 times 3 plus 0 times 2 plus 1 times 1, which is 4. And 1, 0, 0, 1, 0, 1, this corresponds to a 13, this corresponds to a 3, and this corresponds to a 1, so this is 17. So these are valid Fibonacci representations, but if you have repeating 1s anywhere, they're not. So a binary string is a valid Fibonacci representation if and only if you don't have any consecutive 1s in it. And we can similarly define automatic sequences and automata with output over that accept Fibonacci representations of numbers. So instead of in binary, you accept these representations that don't have any consecutive 1s. So for instance, this Fibonacci, this automaton will do exactly the same thing as the Thue-Morse automaton, where it looks at the sum mod 2. but we're looking at the Fibonacci representation of it. And specifically, we can't have two consecutive ones. So whenever we read a 1, the next state doesn't have an output of 1, because if it did, it's not defined on consecutive ones. And similarly, so we can only read a 0 here, and we can read however many zeros we want. Consecutive zeros is fine. But if we read a 1, the only thing we can read after is a 0. And if we do this for every number in its Fibonacci representation, we get this Fibonacci Thue-Morse sequence that looks like this. But it's computed by this automaton, which is Fibonacci, only takes in Fibonacci representations, so we say this sequence is Fibonacci automatic. But it's not k automatic for any k, because we're writing these numbers not in base k, but in this new representation. And if you have a k automatic sequence and you apply it to a and you transduce it, so you apply a transducer to a k automatic sequence, it turns out that the sequence you get is still automatic. So there's still an automaton that recognizes and computes that new sequence. So if we go back, for instance, to these running sums, this sequence, there is some automaton, which I actually have over here, but it's really small because it's really hard to understand. But it consists of 8 states, and if we put in the binary representation of n, it'll tell you what the nth term of the running sum of the Thue-Morse sequence is. But this kind of machinery only works for k automatic sequences and automata that accept base k representations of numbers. And so question is, can we apply transducers to say Fibonacci automatic sequences or other enumeration systems to get another automaton that only recognizes numbers in this Fibonacci representation? And turns out you can. I proved it, but it's still unpublished, so I'm not going to talk about it too much. So yeah. And just to close off, I'd like to talk about like some other stuff going on in the field. So a lot of research in the area of combinatorics on words, which is what I just talked about, is now being done using a software called Walnut, which is written by Hamoud Mousavi, that allows you to input questions written in first order logic and define your own automata, and it can answer those questions and tell you for which values is something true. It actually gives you automata for recognizing whether or not something holds. And this can shorten a lot of long proofs that usually require a lot of ugly casework to just a few simple commands and letting the computer do all the hard work. And last summer, I worked on implementing transducers into Walnut, and they've only recently been added, and there's a ton of applications being found for them constantly. We're finding a lot of new, really cool applications. And because I only recently proved it, applying transducers to sequences that aren't base K, like Fibonacci, that has only recently been considered and mostly still unexplored for the most part, especially doing it this computational way. So in conclusion, automatic sequences are just some sequences that are computed by finite automata. And like how we saw in the example with Legendre's 3-square theorem, a lot of surprisingly a lot of difficult problems that don't look very easy become really easy when you look at them through the lens of automata theory. And if you're sharing something, use the Thue-Morse sequence. It's much more fair. Yeah. Before we get to questions, I'd like to thank some people. So my summer research supervisor, Jeffrey Shallett, who's actually in the audience here today. Hi, Jeff. He's from the University of Waterloo, and his help and suggestions and supervision overall over the past year or so have been extremely valuable. And thank you so much, Jeff. And I'd also like to thank Zach Wolski, who about a year ago, he sent me a paper by Professor Jeffrey Shallett basically saying, hey, Anatoly, you might be interested in this. And turns out I was. So I contacted Professor Shallett, asked him about summer research, and here we are. And yeah, thank you to Parker and Lisa for giving me the opportunity to speak at this seminar. Yeah,
that was a
thank you
wonderful
very
talk,
much.
and very, very awesome. We have a tradition of asking people to fill out a feedback form. You know, we want undergrads to get some feedback on their talks. I can say from my perspective, that was an awesome talk. So let's take 2 minutes and fill out that feedback form, and then that'll give Anatoly a moment to get a drink of water, get a little bit of a stretch, and then we'll take questions after that. So thank you, everyone. If you're about to leave now, I want to say that we do have another seminar next week. We're going to hear about the Topolitz theorem, Topolitz conjecture, which is this square peg and a Jordan curve hole type thing. So that's next week, and that's running on a Wednesday, and it will be hybrid. So that will be next Wednesday at 1 p.m. The details all about the seminar are here. Awesome audience today. Thank you all for coming in. Please fill out that feedback form. We'll take 2 minutes and then take some questions from Anatoly.